Hello everyone, I welcome all of you to this lecture. In last lecture, we have completed flash type of ADC, that is analog to digital converter, and we have seen working principle of that ADC. Also we have seen that flash type of ADC is fastest type of ADC because less time is required for conversion. Now we have to move towards the next type of ADC or analog to digital converter, that is successive approximation type of ADC. Now if you see this successive approximation type of ADC, it is one of the most widely and popularly used ADC technique. This technique uses an efficient code search strategy to complete the n-bit conversion, which is done in just n clock periods. Okay, so how that successive approximation type of ADC is converting that input voltage into digital code, that we have to see. So that's why this is also a faster type of ADC, but it is not much faster than flash type of ADCs, that you have to keep in mind. Okay, so it is little bit slower than flash type of ADC. Okay, now if you see the block diagram of this successive approximation type of ADC, it is shown here. So this is comparator. Okay, again you have to understand the basics of this comparator. Comparator is a op-amp or operational amplifier or a circuit which is comparing two quantities and producing the result as output. Here it is comparing analog voltage VA and DAC output VD. Okay, now this analog voltage is applied to the positive terminal of a comparator, and this VD, which is output from digital to analog converter, that is given to the negative terminal of a comparator. So how it will work, that we have seen earlier. Whenever this VA is greater than this negative voltage, the output of this comparator is 1, and whenever the VD or the voltage which is applied to the negative terminal of a comparator is greater than this positive, the output of comparator is 0. So in short, we can say that the comparator is having two terminals, positive and negative. When the voltage at the positive terminal is greater than voltage at the negative, it will generate output as a 1, and when voltage at a negative is greater than a positive, then what will happen? It will generate a 0 as output. Okay, so here three most important things are used. One is comparator, another is successive approximation resistor, which is most important block in this type of ADC. That's why this type of ADC is named as a successive approximation type ADC. So this is successive approximation resistor is there, that is SAR. And the third important thing is that we required a digital to analog converter. See, this is very interesting. To convert analog voltage into digital one, we require digital to analog converter inside that. This is very interesting thing. Okay, so these three most important things that we are using here. This output of this comparator is connected to the SAR or successive approximation resistor. Now if you see this resistor, it is not your physical resistor which is having color codes. Basically it is a group of flip-flops. I think you may have studied a flip-flop, or you will study the flip-flop in future. The most important application of the flip-flops are the registers. Okay, so these are the digital registers which can be used to store the binary data or bits. So what is the use of this successive approximation register here? They are generally holding the binary bits or a binary data in the form of zeros and ones. Okay, now if you see the SAR output, it is generally in the form of bits, that is D1, D2 to Dn. Okay, and for n bit analog to digital converter, it is producing n bit output, and that is given to the digital to analog converter. and this digital to analog converter is again converting these digital inputs into analog voltage, that is VD, and that is given to the comparator. Okay, so if you see the short working of this analog to digital converter, here we have to send the signal, that is SOC. Okay, so initially it is not in working phase. Initially it is just connected to your other systems. Okay, for example, if you see successive approximation type of ADCs, these are mostly used in microprocessor or microcontroller based systems. So basically these successive approximation types of ADCs comes in the form of integrated circuits or ICs, and in microprocessor or microcontroller based circuits we are connecting these ADCs in that system. So what will happen in that case? Microprocessor will send the, or microcontroller will send the startup conversion signal to the SAR or a successive approximation register. So when this successive approximation register receives the startup conversion signal, it starts converting that analog signal into digital one, and whenever the process is completed, it generates end of a conversion signal. So in this case, your processor or a microprocessor or microcontroller is continuously monitoring this end of conversion signal, and when this end of conversion signal is received by this processor or controller, that processor or controller gets to know that the process is completed, and then it will receive that n bit output code, and it will use that code or that converted signal of analog quantity for its further use, or it will store in a memory. Okay, again I am repeating the process. What happens here? Your processor or controller will send the signal startup conversion. When this ADC receives the startup conversion, it will start the conversion of a analog voltage into digital one. For this process it will require clock signal, and whenever the process of converting from analog signal into digital bit is completed, it produces the end of conversion signal, and when this end of conversion signal is received by the particular processor or controller, what will happen? It will take or fetch the n bit digital output code for corresponding input voltage, analog voltage, and it is taken and it is stored by that particular processor or controller in the memory or system. This is basic use, or this is basic process of using successive approximation of a ADC. But in between this startup conversion and end of conversion, what is the process happens inside this type of a ADC, that we have to see. Okay, now initially if you see, when there is no any analog input voltage, this successive approximation register will produce 000 as output. Now suppose we are having 8-bit type of ADCs. What will happen? This D1, D2 will be up to D8, and all these bits will be 0000. Means what? This D1 to D8 bits will be 0. Okay, so as soon as the analog input voltage is applied, and as soon as we apply the startup conversion signal to this successive approximation register, what will happen? It will set its MSB bit as a 1. Now listen carefully what I am trying to tell you, because this process is very important. This can only give you the information about this working principle of a successive approximation type of ADC. Initially SAR's output is 0. Okay, means suppose we are having a 8-bit type of a successive approximation register type of a ADCs, then D1 to D8 will be 00000000, and when analog input quantity is applied here for the conversion, and as soon as your processor or controller sends the startup conversion signal to the SAR, when SAR receives that, it starts the conversion, and the first process that it is doing, that is it is setting the MSB bit as a 1. Okay, so for 8-bit type of ADCs, it will set the code here as a 1 0 0 0 0 0 0 0. Okay, so this bit is called as LSB and this bit is called as a MSB. So MSB will be set to 1. Okay, so for that particular code, this DAC will convert that digital input into analog voltage. This is the working of this digital to analog conversion. That particular voltage for the respective 8-bit code is given by VD, which is analog voltage, and that voltage is compared with the help of a comparator to this analog input voltage. Means this VA and VD is compared with the help of this comparator. Now if VD is less than VA, listen carefully what I am telling to you, or when VA is greater than this VD, the meaning is that the code which is generated for this VD or the VD which is generated for this code is now less than this VA voltage. So we have to just set the next bit as to 1. Means initially we have set MSB as a 1. Now that is again less than this VA. That's why this VA we can say is greater than this VD. So that that's why we have to increase this VD and again we have to compare with this VA. So to this increase this VD, what we have to do is that we have to just keep this MSB as a 1 and we have to just set this D2 from 0 to 1. So we will get the output voltage of this SAR is a 1 1 0 0 0 0 0 0. Okay, so this will happen here. Okay, so it is happening as per the upcoming clock cycles, that you have to keep in mind. This is very important. This operation is done with the help of this clock periods. So single bit setting is done for a single clock. Okay, that you have to keep in mind. That we will see afterwards, don't worry. Now again that code is 1 1 0 0 0 0 0 0, that is compared with this analog voltage. That is the first case. But suppose if previously that the code that we have generated, that is a 1 0 0 0 0 0 0 0, is now greater than this VA, means what? This VD is suppose greater than this VA. What will happen? The reverse process is done. In that case, that 1 is set to 0 and next bit is set to 1. Okay, now to better understand this, let us see one example and then you will understand how the process is done. Okay, now suppose we have the 8-bit successive approximation ADC. Again I am repeating, initially SAR output is D1 to D8, that is a 0 0 0 0 0 0 0 0. So that's why the VD is a 0, because as the 8-bit inputs are 0, VD is a 0. Now this 0 is applied here, and as 0 is applied here, what will happen? Comparator output is 1. Okay, and as soon as we receive the startup conversion signal, and as the comparator output is 1, what will happen? It will set this MSB bit as a 1. So if you see what will happen, new SAR output will be what? And this MSB will be 1 and all other outputs, inputs will be 0. Now we are comparing VD with VA. Okay, so this 1 0 0 0 0 or that this code, that is 1 0 0 0 0 0 0 0, that is applied to DAC, and from that DAC we are getting a VD proportional to this digital input. And now if that VD is less than VA, means the comparison is done with this comparator, and now if this VA is greater than VD, what will happen? We can say that still we have not reached to this value, and therefore the comparator output is 1, and that's why this SAR will make this D2 as a 1. So what will be the new code? The new code will be 1 1 0 0 0 0 0 0. Okay, again that code again is compared with this one, but before that it is converted into VD. Again this VD is compared with VA. Again if you say this VA is greater than this VD, then again we are not close to VA, as VD is less, which is equivalent to this code. So what will happen, comparator output will be 1 again, and again we have to make this next bit as a 1. So what will happen, this next code will be what, 1 1 1 0 0 0 0 0. Okay, so the most important thing that you have to understand is that whenever this VD is less than VA, or VA is greater than this VD, we just go on making this next bits as a 1 1 1, means just we are increasing the value of this 8-bit code to make a closer value of this VA. That operation is done. But what happens when that code is greater than, or that value is greater than VA, that we have to see. Now it is explained in this case number 4. Now suppose this code is generated by this successive approximation register, that is 1 1 1 0 0 0 0 0. Now for this particular code, this DAC will generate VD, and this VD is now compared with VA. Now suppose this VD that we have set now with the help of SAR, suppose it is greater than this VA, what will happen, comparator output will be what, 0. Now when comparator output is a 0, then SAR will understand that as comparator output is a 0, this VD is greater than VA. Now what we have to do, we have to do this reverse process. Reverse process means what, we have to just make this D3, which we have earlier make as a 1, that to the 0, and next bit to the bit to as a 1. Okay, means what, if suppose this VA is still again greater than VD, we will make this D4 as a 1. But here VD is greater than VA, the reverse process we have to do, that is we have to make this 1 as a 0 and next bit as a 1, means we have to decrease this count. Initially we go on increasing this count, then but now as VD is greater than VA, again we have to reduce that VD. So that's why we have made this 1 as a 0 and this 0 as a 1. So if you see the next case that we have got here, as the VD is greater than VA, we have got this new code, that is 1101. This previously 1 is made as a 0, and this 0 is made as a 1. So now you can say that this code is less than this code, means value of this code is less than this code. Okay, I think you got this idea. Again this code will be converted into equivalent VD voltage by DAC, and it is compared with analog voltage. And if it is again VA is greater than VD, now here VA is greater than VD, what we have to do is comparator output we have to make as a 1. Now here some mistake is there. Here you have to make this comparator output as a 1. Okay, so this is printing mistake, this you have to understand. So VA is greater than VD in this case. So what will happen, what we have to make is that we have to make the next bit as a 1. Okay, so this next bit is made as a 1. Again I am repeating, this is a 1, it is a printing mistake, you have to make a comparator output as a 1. Okay, now new SR output will be 1101 1000. Now this process will continue as like this. Now suppose the next bit that suppose the VD is again greater than VA, the next value, this value. So what we have to do is that we have to make this D6 as a 1 and D7 as a 0. Okay, so here D5 is made as a 0 and D6 is made as a 1. Here D5 is made as a 0, D6 is made as a 1. I have told previously the next process, sorry. So as VD is greater than VA, what we have to do is that make 1 as a 0 and this 0 as a 1. Similarly, again if VD is greater than VA, what we have to do is that make D6 as a 0 and D7 as a 1. Okay, so we have to do this process. Still this all the bits or 8 bits process comparison process is completed, and when this bit is covered, the conversion is covered, then what will happen, we can consider that VD is equal to VA and this process is completed. Okay, so this is the 11010010. This is the output code that is generated for a VA. Okay, so for example purpose only we have taken this 11010010. Okay, you can take any value, no problem. But one most important thing you have to keep in mind that is whenever this VA is greater than VD, we have to make next bit as a 1. Okay, and whenever this VD is greater than VA, we have to make the current bit as a 0 and next bit as a 1. Okay, means when VD is greater than VA, we have to just decrease that digital count, and whenever the VA is greater than VD, we have to just increase that digital count so that we can match the value of a VA. So this process is done till this 8 bits or n bit completes, and at the end the SAR will hold the actual 8-bit code or n-bit code with respect to that analog voltage, and whenever the process is completed, this SAR will generate end of conversion signal. Okay, and whenever this end of conversion signal is monitored by this processor or controller, which is continuously monitoring or continuously waiting for the signal, then when it receives the signal, it will take a output code or 8-bit output code in this case from these lines directly, and this SAR will finally hold the value and the process will be completed. Okay, and whenever we have to start the new process, what we have to do is that we have to send the start of a conversion, then this process will complete, conversion will complete, and it will generate end of conversion signal. Okay, so that's why this successive approximation type of ADC is very famously used in system design. In third year or in last year, you may use analog to digital converters. There is one very famous IC which is used in the system, that is IC ADC 0809. That IC is using this successive approximation type of ADC. You can search on internet IC ADC 0809. You can take down, search that ADC, you will get all these control signals on pins, that is start of conversion, end of conversion. Okay, and the output digital codes, then input voltage, all the signals you will get on that particular IC. Okay, so just search the datasheet of ADC 0809, and for more understanding please refer that datasheet how it is converting. You will get this diagram inside that datasheet. Okay, so this process I have explained here. Okay, I suggest again you please revisit this video and carefully see this process how it is done. Just one mistake is there, this comparator output must be 1 here, that you have to keep in mind. And if you see this video again, you will understand this. If you have any doubt, you can contact me, no problem. Okay, now let us see the advantages and disadvantages of this successive approximation type of analog to digital converter. So the advantage is that conversion time is n clock cycles for n bit ADC. Okay, what is the meaning of this one? Let's understand the same example. Suppose you have 8-bit successive approximation type of ADC. Okay, so it will work with comparator, SAR, DAC, no doubt, but this function is synchronized by this clock. Okay, and for n bit type of ADC you will require n clock pulses. Means what? The conversion of this ADC is done with the help of clock cycles, and when you are using 8-bit successive approximation type of ADCs, it will require 8 clock signals to convert this process or convert this analog voltage into respective digital voltage. Okay, so that's why I can say that the conversion time is very less. Just that number of a clock cycle required for particular ADC which is having n bits. Means what? It will require n clock cycles for n bit ADCs. That's why I can say that it is a faster. Okay, so what is the disadvantages? not faster than flash type of ADC. Yes, it is a faster, no doubt, but it is not fastest, because earlier we have discussed that flash type of ADC is fastest type of ADC. And secondly, again the circuit is complex. Okay, why complex? Because previously we have seen that ADC requires DAC for the conversion. Along with that, it requires SAR, comparator, then this clock signal, then this startup conversion, end of conversion, signal generation circuitry. Okay, so if you see this, even if it is looking like a simple diagram, internally it is complex. Okay, so that's why I can say that, or we can say that the circuit is complex. Okay, so this is all about this successive approximation type of ADC, that is analog to digital converter. So two most important types of ADCs we have completed till now. So again there are another types of ADCs that we have to see in upcoming lectures. So for today this much is sufficient. Okay, so in next lecture we will see single slope type of ADCs, which is also called as a RAM type ADC. Okay, the meaning is same, single slope you can call as a single slope, or you can call it as a RAM type of ADC. Okay, so the working of this single slope or RAM type of ADC we will see in a next lecture. But till now, two types of ADCs we have completed. You have to just revisit my video which is on YouTube and just see how it is, how the data is converted with the help of these two types of ADCs, that is analog to digital converter. So these two types we have completed or covered. So in upcoming lectures we will complete this, we have completed flash type of and successive approximation, which are very famous, and this middle three are remaining, single slope, dual slope and staircase RAM, that we will see in upcoming lectures. Okay, so in next lecture we will start with this, that is a single slope RAM type of ADC. If you have any doubts you can ask me, no problem. So today we will stop here. Let's meet in a next lecture. Thank you.